In this video, we will address some frequently asked questions concerning sensitivity analysis, and we'll use our favorite example for that.
You're kidding, right?
And here we have the formulation, graphical solution, step 0 tableau. So let me mark it step 0. Then this is the optimal tableau. But in general, this can be the tableau after any step of the simplex method. And here we have the formulas that are central for this part of the course. So these formulas relate the simplex tableau at any iteration of the simplex method, including the optimal one, to the original problem data, to what you see at step 0. And one of the major points of confusion seems to be where exactly we read all this data, like B inverse times N, and from which table. So typically in a standard sensitivity analysis problem, we are given the linear program and then we are given the optimal tableau. And even if we are not given the optimal tableau, then we can use these formulas here to reproduce it. Remember, we discussed how to do it using Octave. You just need to know what variables are basic in your optimal solution. So once you have that information, you can read your matrix B, matrix N, and the rest of the parameters that we use in these formulas, such as CB, CN, B. All of these can be read from the initial tableau. And the initial tableau is easy to construct based on the original problem data, right? So once I know which variables are basic, I can easily extract all of this from my step 0 tableau. For example, for the optimal tableau, we have the list of basic variables given here. They're S1, X2, X1, and S4. So for me to construct the matrix B, all I need to do is go back to step 0 tableau and extract the corresponding columns from step 0 tableau. So we had S1 was one of the basic variables, then X2 was the second one, X1 is one more basic variable, and S4 is the last one. Okay, and typically the way we would extract this matrix B from our step 0 tableau would be in the order of columns that we have in this tableau, right? So our first column will be for X1, the second for X2, the third for S1, and the fourth for S4. And what's important when we use these formulas here is to preserve this order. So usually we need to stick to the order in which we list variables, all right? And not following the order is one of the common mistakes made when the order in the optimal tableau is arbitrary and is not the same as it is in the column. Because, you know, we can list the basic variables arbitrarily in our tableau. The tableau is still correct. But if you want to read the information specified here in these formulas directly from our tableau, we need to make sure that the order that we have for the columns coincides with the order that we have for the rows. Only then can we guarantee that we can read B inverse from the columns corresponding to the slack variables and B inverse times N from the columns corresponding to the non-basic variables. Alright, so that's why the first thing we do when we get the optimal tableau, first we need to figure out what are the basic variables and in which order they are listed. So you may not be given the list of basic variables in the problems that I give you, but they're easy to figure out based on the tableau. So first you specify this column of basic variables here, and then you look at which order the basic variables are listed. So you need to make sure that that order is the same in which they are listed in the columns. If you arrange them properly, then the columns corresponding to the basic variables will form the identity matrix, and as a result, B inverse will be located in the columns corresponding to the slack variables. Alright, so currently we see that the variables in the basis are not listed in the right order. Therefore, first we rearrange them by putting the row for x1 first, then for x2, then for s1 and s4, and as a result we'll obtain this correctly arranged tableau. So now you see that the order of the basic variables is exactly the same as it is in the columns, and because of that, if I extract now the columns corresponding to the basic variables, they will form the identity matrix. And now by the Gauss-Jordan rule, we can read our B inverse from the columns corresponding to the slack variables, because what happened here, the columns corresponding to the slack variables were originally forming the identity matrix, but then after we applied several elementary row operations and transformed our tableau to this one, now the columns corresponding to the bases form the identity matrix, and because of that, by the Gauss-Jordan rule, the inverse of B must be located at what used to be the identity matrix, the columns corresponding to the slack variables. And I want to emphasize that it doesn't matter whether the slack variables are basic or non-basic here, you will have B inverse in these columns corresponding to the slack variables. For example, here we have S1 and S4 are basic variables, S2 and S3 are non-basic. That doesn't matter. Whether they're basic or not is irrelevant. This part of the tableau contains your B inverse. Alright, so once again, B inverse for the current basis is located in the columns corresponding to the slack variables in the current simplex tableau, not in step 0 tableau. In step 0 tableau you read B inverse is in the current tableau. Now the other useful matrix that we can read from the current tableau is B inverse times n. So B inverse times n, according to our formula here, is located in the columns corresponding to the non-basic variables in our tableau. So I just need to figure out which variables are non-basic, since x1, x2, s1 and s4 are basic. Whatever remains will be your non-basic variables. And the only remaining variables would be s2 and s3. We can conclude that this matrix right here is your B inverse times n. So again, this is the matrix that corresponds to the non-basic variable columns in the current tableau. And you can see that this matrix is 4 by 2, so it has 4 rows and 2 columns. In our case, we only have 2 non-basic variables, so this dimension of the matrix is correct. So in this case, we of course approach the question of extracting this matrix that we need differently from when we looked for B inverse. Remember, with B inverse, we always look at the slack variable columns. With the matrix B inverse times n, we'll look at non-basic variable columns. And what are the non-basic variables? It changes from iteration to iteration. So you always need to extract this matrix from the columns that are non-basic, and in our case these non-basic variables happen to be both the slack variables, and our matrix is in fact a sub-matrix of B inverse, but this is just a coincidence in this particular case. So to summarize, this is the process that we follow. First, we arrange the rows in the tableau so that the basic variables are listed in the same order as in the columns. In some cases, this may be the order you are given to start with, whereas in others you need to do some preliminary work before you can read the matrices that you need. And then once you've done this, then second, depending on what case you are analyzing, when we are analyzing the change in the objective variable coefficient, then we typically need to extract B inverse times n. This will be the columns of your tableau corresponding to the non-basic variables. And then if you need to extract B inverse, which we typically need for analysis of the cases when we change the right-hand side, then this corresponds to the columns of the slack variables. So this is all I wanted to say regarding extracting the matrices that we need in sensitivity analysis. And then I wanted to discuss another minor issue that seems to be more of an issue than I would have thought it would be, but I think we need to address it. So when we solve the inequalities to ensure the proper sign for either row 0 coefficients or for right-hand sides, we typically obtain systems of inequalities for delta that could be something like this. Let's say delta is greater than or equal to -5 and delta is greater than or equal to -3. Alright, and quite often I see incorrect solution to this system given by delta between -5 and -3. Obviously this is wrong, so whenever you solve the systems of inequalities involving just one variable, I recommend you to plot your solution on a real line, because that is something that is easy to do in this case. So for example, for our case, if we plot -5 and delta greater than or equal to -5 corresponds to this part of the axis, and then let me use another color for the other inequality. We have -3 somewhere here, let's say, and the points corresponding to delta greater than or equal to -3 are located here. So this is the axis for delta. And clearly the solution will be the intersection of the two, so your solution is obviously delta greater than or equal to -3. So your range for delta would be between -3 and infinity. And in particular, when we are talking about the right-hand sides, this situation is common when we change the right-hand side of a constraint that is not binding at the optimum. For example, if we look at this line right here, it doesn't pass through the point of the optimum, so clearly I can move infinitely large distances to the right, and this will not affect the feasibility or optimality of point C. So you expect to have an infinite range for a constraint that is non-binding, because you can move at any length to the side opposite of the point of the optimum.
I think it's working!